Hello again, and this is the second session that I was talking about uh, for the rigid body equilibrium in 2D. This is another example that I didn't want to pick examples that are pretty straightforward, like simply supported beam, a hinge and a roller, and that's it. So last time we looked at a 2D member, and we said that's why we didn't have four unknowns, but only three. And here we have something similar. So this is a beam that is connected here by a pin. That's two unknowns. And then we have a cable that goes through a pulley and it's attached at two locations. And there is a mass here of 80 kilogram that was held by that contraption. So um, how many unknowns do we have? Without, without thinking, if it's anything other than three, you won't be able to solve. Either it's if it's less than three, it would fall down. If it's more than three, it's statically indeterminate. So we know the answer is like I close my eyes and say three. Where is the third? The tension in the cable. Notice that this, even if they don't tell you, it has to be a smooth pulley, meaning there is no friction. You say, how come there is no friction? Yeah, there is a very small friction, such that the tension in this part of the cable is the same as the tension here. Of course, it's not the same. There is some friction here, but if we say that's a smooth pulley, that's another way of telling you, oh, there is a friction, we know, but you can ignore it. It's so small. Like here, we don't show you G or center of mass or center of gravity. It means, yeah, we know this beam has a mass, but it's small, so you can ignore it. Okay? So how do I draw a free body diagram of this shape or of this beam? We are going to draw the beam as a line like we always do. The pin is replaced by an X and a Y. So A sub X, A sub Y. By the way, some people draw the A sub Y above and the A sub X inside. I prefer to do it this way because I want you to see the two arrows. If I draw A sub X here, maybe I use a different color or something, but I don't like it. And notice that a force, even though a force is not a free vector, but it's a sliding vector, meaning as long as I don't change it, whether I draw it here or I draw it there, it is the same. Okay, so it's just a matter of taste. I prefer to draw it outside of the body. Some people draw it inside the body. It's it's not a big deal. Then I have a tension. Notice that a free body diagram, I keep saying that, meaning I have to free the beam from everything else. It is connected by a hinge, so I take the hinge and replace it by the reaction. It is attached to a cable, so I cut this cable. Notice when you cut the cable, you see two forces. Internal forces always come in pairs. So you see a force that is pulling the beam from falling, and another tension here that is the one keeping the beam from falling down. And the other tension is pulling, it's like pulling back. It's the opposite, right? And also at E, there is the same tension. It's not a different one. Don't say T1 and T2. No, they are the same. If they were different, you won't be able to solve. Take the pen, try it. Three equations, four unknowns. No way. Okay, so we know the slope here. Again, they tell you 3, 4, 5. 3, 4, 5. What else is missing? There is a mass here. of 80 kilogram, but these are forces, not masses. So you have to write it as a vector, which means you would multiply. Notice that point D here is irrelevant for me. I'm not gonna, I don't need it. We can show the dimensions and say this is 2. This is 2. I draw it very far away, so maybe I needed to make it slightly to the left. Anyway, it's not to scale. If you can do it uh, to scale. So you multiply that by 9.8. You can say 9.801. Again, approximation, guys. Y- We don't know the exact value of the the Earth acceleration. It depends where you are. And you don't have like measuring measuring system that are so accurate. So it's just don't make it a big deal. Some people even in high school, I know you use 10, right? 10 is a little too much, but 9.8 or 9.807, where are you located? Are you above a mountain or a valley? Is it in the United States or the equator? It's like, what are you talking about? The point and the zero cancel, and you get like 8 times 98, right? So 700 and oh, okay, I'm sorry. 784 Newt. And there is no more forces. What's still missing? Yes, the coordinate system. I'm going to use the horizontal as X and the vertical as Y. In other problems, especially when we start working with friction on inclined surfaces, we may use the incline as our x and the normal to it as the y, because most of the forces are either on the incline or on the normal. So it doesn't make sense to use x and y as horizontal. Here, most of these problems we use x as horizontal, y is vertical, but it's not guaranteed. I don't know. You have to tell me. So that's why um, you have to show it on the free body diagram. Otherwise, it's not free. What else do we need? Is there anything else? No. So now I can start working. Remember, we have three equations of equilibrium. Summation of the forces in the x equals 0, summation of the forces in the y equals 0, and summation of the moment about any point in the plane is 0. So if I take summation of the forces in the x, this tension has an x component and ax. So these are two unknowns. If I say summation of the y, I have a, I have t, and another component of t, two unknowns. So most likely, as many as, as we have in many problems, uh, I should start by taking the moment. Okay, you take the moment where at least not at least, two forces intersect. It doesn't make sense to take the moment about C because the T will have a moment about C and the A sub Y has a moment about C, still two unknowns. Yes, you can have two unknowns and two unknowns and two unknowns and solve three equations and three equilibrium equations and three unknowns, but why would you do that simultaneously? It doesn't make sense. So you have to think a little bit. If I take the moment about point A, I can solve for T right away. T is the only unknown. Yes, I have two T's, but it's the same unknown. In fact, is there another point you can take the moment about? No? I don't think so. Because if you say about B, then AY has a moment and this T has a moment. If you take the moment about E, then this force produces a moment and AY produces a moment. So in all cases, I will have to start with the summation of the moments about point A equals 0. And as I said, some people would do that, meaning I'm taking counterclockwise as positive. You don't need it because that's a universal convention, is that counterclockwise moment is 0, is positive. Okay, so now I have the 784 is rotating clockwise and the t's are rotating counterclockwise. So this t times 2 is positive. And 4/5, you see the vertical is 4 out of 5. 4/5 of t times 4 is also rotating counterclockwise, so it's positive. So even though it's one unknown, it's producing two different moments about point A. Okay? Now, minus. So instead of saying this plus minus, we can simply say equals, right? You move it to the right-hand side and you say equals 784 times 5.5, right? 4 and 1.5. And now you can use the calculator. You say 16 over 5. So this is 26 over 5t. 2 is 10/5. And 4 times 4 is 16/5. And 10/5 plus 16/5 is 26/5 equals the 784 times 5.5. So from here you can solve for t by multiplying these two and then multiply by 5 over 26. So what we did is say 80 kilogram times 9.8. So we got the 784. We're going to multiply it by 5.5. That would give me the right-hand side. And then I'm going to divide by 26/5 or multiply by 5 and divide by 26. It's the same thing. So that will tell you 829 Newton. We could say 830. But 8:30 may be a little too late for you. You hate dead jokes, I know. So I'm giving you a hard time here. But now once you know the t, you can solve for either x or y. It doesn't matter. I know, I was telling you, some people always start summation of the force in the x equals 0, then y equals 0, then z equals 0. No, don't memorize. There is no one like a silver bullet, right? So in this case, we started with the moment because it made sense. Summation of the forces in the x equals 0. And as I said, some people would do that, but everybody uses the right for x is positive and the left is negative. I have a sub x going to the right, so it's positive, minus 3/5 of the tension is going to the left, so minus 3/5. But instead of saying minus, I can say equals 3/5 of the tension, which is 829. So from here, I get a sub x would be to the right, of course. Okay. Here I didn't say the direction of t because here it's vertical up, here it's inclined, so there was no reason to say up, but it would be incorrect. If I say inclined, it's incorrect. So I have two locations where there is t. But a sub x, oops, what did I do? A sub x, I will take the tension that I have here and multiply it by 0.6 or by 3 over 5. So you get 497.5 Newton to the right. And finally, you take the summation of the forces in the y direction and you equate it to 0. And again, as I said, some people do that to tell you that up is positive, down is negative. I have a sub y is going up, t is going up. The other t, 4/5 of it, is going up. So of course, AY is negative, it must be going down. Of course, if these tensions, oh, I'm sorry, I didn't subtract that. But of course, the two tensions are pulling up they are more than this weight as their sum. So the A sub y must be going down, or else the beam would have moved. Okay, I'm sorry, I forgot to say minus 784 equals 0. So now A sub y would be negative. In fact, I'm going to take the tension and multiply it by 9/5. That's negative, right? Here is the tension. So instead of saying the tension plus the tension times 4 over 5, it's just 9 over 5 or times 1.8. Times 1.8. And then I'm going to, that's a negative, of course, but I wrote it as positive. So I'm going to subtract 784 and enter the answer as negatives. Negative 708.6 Newton, which is 708.6 Newton down. And basically that's it. These are the reactions, AX and AY, and that's the tension. And again, if you have time, it is always a good habit to say, take the moment about another point and see if you get 0. For example, if I take the moment about point C, you see, if I take the moment about point C, I get 4/5 of T. Here is 4/5 of T is going clockwise times 1.5, so times negative 1.5. I also have this T going clockwise, so it's negative minus the same T times 3.5, and then plus AY, which is the 7.08 times 5.5, just to check our, oops, I didn't say that, times 5.5. I got 0, 6 times 10 to the negative 8. So that's a quick thing to make sure that the numbers make sense and they are correct. Okay? So again, we drew a complete free body diagram with dimensions. Why did I draw the dimensions? Because I used them. I used the 2, I used the 4, I used the 5.5. If I'm not going to use something, I don't need to show it. I used the weight, so I had to show it. Okay? Sometimes, and I had to show 3, 4, 5 because again, I multiply by 4/5 and 3/5. Anything that you write here should show up there. I said summation of the moment about A, so I have to show point A. Summation of the forces in the X, I have to show my X. I have to show my Y. Okay, I hope this was good enough. And I think that's enough on rigid body on 2D. Next time, probably we'll have a section or a session on the types of supports in the 3D, and then a different one for analyzing 3D rigid bodies so that it doesn't become very long like today's previous lecture. I hope this was helpful for you, and I wish to see you soon. Thanks and have a great time.